We're going to discuss logarithms and some unique properties that they have about expanding and condensing. So we're going to take some notes on that. First, I've taken a screenshot of the day one notes on exponent properties, and we're going to take note that logarithms are actually the inverse operation of exponents, but we can also think about them as an exponent. And here's what I mean by that. If you see that a to the b equals c, the way that we would write that in logarithmic form is we would take a log base a of both sides, and we would end up with log base a of c equals b. Well, notice what was going on in this exponential. B was the exponent. So that means that this entire log represents the exponent, whatever the exponent's numerical value is. That's log base a of c. So a to the something equals c. Well, that something is log base a of c. So what that means is if I'm thinking about these logs essentially are making up an exponent for some kind of exponential function. And so if I think about exponential functions, if I have an exponential function where the exponents are added, remember that log base b of x and log base b of y represent exponents in some exponential function. If the exponents are added, that's the same thing as saying I can multiply the two um, the two things together, basically. And so this product rule indicates that if I have log base b of x plus log base b of y, I can rewrite that as log base b of xy. So I can take these x and y and I can multiply them together. Um, Real quick, a small proof of why that would work. Um, Very small proof. If I take b to the log base b of x plus log base b of y, so I have b to all of this, that's going to be rewritten as b log base b of x times b log base b of y. And I can do that because of this product of powers property. Then b and log base b are exponents. So what that means is they basically end up canceling. Same thing over here. So now I have x times y. Now remember, what did I actually do? This is not identical to this. I took b to the log base b of x plus log base b of y. So the way I can go back to what I originally did was, since I took b to both sides, I would then have to take a log base b to get it back to what it originally was. So log base b of xy is identical to the original equation or original expression. So since that's true, that's kind of a mini proof of why it works. Um, but you don't have to necessarily write it down, and I'm not going to do that proof for the rest of them. I just kind of wanted to show you that if I thought about it, it would actually work out. Okay, the quotient rule works very similar. So if the exponents are subtracted, I can rewrite this with the base of x to the a divided by x to the b. So now if we look at this quotient rule down here, log base b of x minus log base b of y, I can write that as log base b of x divided by y. And then the power rule, well, if I'm looking at the power rule, x to the a to the b is equal to x to the ab, that's power of a power. Now, if I'm looking at this, I'm actually going to do a small, quick proof of this one. But if I have log base b of x, and I multiply it by a, that's the same thing as having a consecutive log base b of x's added together. So there's a of these. Okay, so that's kind of what's going on there. Now, if I want to, take this to like a quick, brief understanding of what's going on using numbers, I'll do two quick examples. Log base 2 of 4 plus log base 2 of 8. Well, log base 2 of 4 is log base 2 of 2 squared. And log base 2 of 8 is log base 2 of 2 cubed. So I know by this product rule that I can rewrite that as log base 2 of 2 to the 5th, which is log base 2 of 32. And both of these are equal to 5. So essentially what's going on here is if I have this number and I have some kind of like 5 out here, I can rewrite this in the front because 5 times log base 2 of 2 is going to equal 5. So let's just let's do it in another context real quick. If I have log base 3 of 8, that's the same thing as log base 3 of 2 to the 3rd, which is the same thing as 3 times log base 3 of 2. I can take this and move it to the front. Now, why ultimately is that? Because if I take this little thing that I had over here and I apply, so I just use some examples, but if I apply the rule that I had over here with the product rule, what I can do is I can rewrite this as log base b of, if I add a copies of them, I would end up being able to put them inside of the log all multiplied together. So log base b of x times x, a copies of that, which is the same thing as log base b of x to the a. So this is the power rule. Now let's do some examples. Condense. All of these are log base 5s. So anytime I see a plus, I'm going to put it on the inside and multiply. Anytime I see a minus, I'm going to put it on the inside and divide. So I have, well, I guess the first thing I have to do is see that I have this 2 here. So I'm going to rewrite log base 5 of x, well, 2 times log base 5 of x. I'm going to rewrite this as log base 5 of x squared. And now I can do the problem. So 8's going to go in the numerator. X is going to go in the numerator. 4 is going to go in the denominator because I have a minus. And then this is a plus, so x squared is going to go in the numerator. So the final answer would be log base 5 of 2x cubed. That's condensing it because 8 divided by 4 is 2. Okay, now in this problem, log base a, I'm going to rewrite this with the 3 and the 4 back inside. So log base a of 4x to the 3rd minus log base a of 2x to the 4th. So now I can simplify this. Log base A of 64x cubed over 16x to the fourth. And then I can write a final answer, log base A of 4 over x. So that's just condensing. Now expanding is doing it in the opposite direction. So log base B of 5, x to the 7th, z, all of these things are multiplied on the inside. That means I can turn them into pluses with separate log base b's. So log base b of 5 plus log base b of x to the 7th plus log base b of z. And then the final thing I'm going to do is I'm going to take this 7, that's an exponent, and I'm going to turn it into a number that's being multiplied on the outside by the power rule. So log base b of 5 plus 7 log base b of x plus log base b of z. Log base b of 3x to the 5th over 7y to the 4th. Log base b of 3x to the 5th minus log base b of 7y to the 4th. And now I have to kind of be, well, I have to really be careful. I can't just take this 5 and move it to the outside because it's not the whole thing being taken to the 5th power. So this may not have been the most efficient way to do this because I'm going to have to separate this even more. So log base b of 3 plus log base b of x to the 5th minus log base b of 7 minus log base b of y to the 4th would be a little bit more, probably a better way to have started, but at least we figured out how to get there in due time. So log base b of 3 plus 5 log base b of x minus log base b of 7 minus 4 log base b of y is the final answer. And that comes from taking these exponents and moving them down to be coefficients. Now finally we have this log base 7. Notice that 8a is being an exponent for the entire inside. So I can do 8a, moving it to be a coefficient right away. Log base 7 of 5x. Then I can have 8a log base 7 of 5 plus 8a log base 7 of x. And that would be my final answer because I can use the product rule to separate those. Couple of log equations using expanding and condensing. So with this minus sign means that I can divide. So log base 4 of x over 7 equals 3. So I can turn that into a minus, or I'm sorry, I can turn this subtraction of logs into a division on the inside. Then I can use the properties of logs that log base 4 of x over 7 equals 3 means that 4 to the third is equal to x over 7. So x over 7 equals 64. And then x equals 64 times 7, which is 448. Problem 2. All of these have base x plus 5, so I can condense these. Log base x plus 5 of 6 times 2 divided by 3 equals 2. 6 times 2 divided by 3 is 12 divided by 3, which is 4. So log base x plus 5 of 4 equals 3. So x plus 5 to the third power is equal to 4. Now I have to solve for x. So I'm going to take the cube root of both sides. So x plus 5 equals the cube root of 4. I do not need to put a plus or minus when I take a cube root. And then I'll subtract 5. So x equals negative 5 plus the cube root of 4. So that's my final answer for x. And again, you can substitute all of these x's back into the original problem and make sure that they all work out. Um, and just kind of double check your answer. So let's condense this. Log base 8 of x to the 5th times 32 equals 2. Remember, I can move this 5 up. So 8 squared equals 32x to the 5th. 8 squared is 64. So 64 equals 32x to the 5th. Then divide by 32. So x to the 5th equals 2. And then I I take the 5th root of both sides, and I don't have to do a plus or minus with any odd powered root. So x equals the 5th root of 2. Finally, I have a plus here. So natural log. Remember that natural log of x is equivalent to log base e of x. So this is really just log base e. So natural log of x times x plus 1 is equal to natural log of x squared plus 3. Now, since both of these are on the inside of a natural log, I actually don't have to do what I did in the first 3 problems. If they're both on the inside of a natural log, they have to be equivalent. So x times x plus 1, or x squared plus x, must be equal to x squared plus 3. So then I subtract the x squareds from both sides. They cancel out, essentially, and I get x equals 3. Now, in order to make sure that this actually is true, I have to plug 3 back in and make sure that I don't get any negative numbers on the inside of a natural log or any log of any kind. But it ends up working out where these all work out, and all of these numbers never give us any negatives on the inside of a natural log.